The demand for reliable gas monitoring systems is growing to help ensure the safety of employees who work in potentially hazardous environments where toxic gas may be present, as well as ensuring the safety of the general public. Industries in which toxic gas sensing is used include oil and gas exploration, chemical processing plants, hospitals, semiconductor manufacturing facilities, and sewage treatment plants. Some homes and commercial businesses also implement gas monitoring, especially in enclosed areas such as parking garages and tunnels. This webinar will review how these gas sensors work and the associated circuitry required to control and manage the sensors. Both 2- and 3-terminal electrochemical gas sensors are in use today. A 3-terminal gas sensor is shown here, consisting of a sensing electrode, a reference electrode, and a counter electrode. A 2-terminal sensor functions the same way, but does not have a reference electrode. As the target gas passes through the membrane, it reacts with the surface of the sensing or working electrode, causing either an oxidation or a reduction. If the sensing and counter electrode are connected on the outside of the cell, a current will flow that is proportional to the amount of gas concentration. The reference electrode is used to provide a stable voltage potential for the sensing electrode to maintain good linearity and minimize sensitivity to the interfering gas. Now that we understand the fundamentals of how a gas sensor works, let's explore the external circuitry required to properly measure the current that flows between the electrodes and to provide control for the sensor. This circuitry is called a potentiostatic circuit and serves 3 main functions: control, current measurement, and biasing. A typical potentiostatic circuit is shown here, which we will now explore in more detail. The first function of the potentiostatic circuit that I mentioned is control, in which the circuitry maintains the proper voltage between the reference and the working electrode. The control circuitry provides current to the counter electrode in order to balance the ionic current that is flowing from the counter to the working electrode. There are several critical parameters to consider when selecting the proper amplifier to use in this control loop. Any offset on the amplifier will cause a shift in the working electrode's potential when the circuit is switched on. Since these sensors are highly capacitive, a small shift in potential can create large current flows. Hence, low offset and low offset drift is important. The control amplifier should not draw any current from the reference electrode. Hence, a low bias current is also required. Finally, the output of the control amplifier drives the counter electrode and hence needs sufficient voltage swing to drive the counter to the required potential and with sufficient current. The second function is to accurately measure the current that results from the presence of the target gas. This is accomplished via a transimpedance amplifier circuit, which converts the current to an equivalent voltage, along with some gain and filtering. For the measurement amplifier, low offset is again important, as any offset error will contribute to the measured current. Low bias current is also critical, as this will create another source of error in the current measurement. Finally, the generated current from the gas sensor can be bidirectional, depending on if the reaction is an oxidation or a reduction, so the measurement amplifier must be able to handle sinking sufficient current. Finally, it is common to implement a field effect transistor, or FET, that shorts the reference and working electrodes when power is removed. This ensures that the sensor will be ready immediately once power is reapplied. If the sensor is left open circuit when powered off, it could take a few hours for the sensor to stabilize once power is applied. Microchip offers a wide variety of operational amplifiers that are well suited for interfacing with both 2- and 3-terminal gas sensors. The MCP6032 precision amplifier provides low initial input offset and a CMOS input structure which enables low bias current. The MCP6442 operational amplifier provides a more cost-effective alternative, providing an even lower power solution, but with a higher input offset error. For a more highly integrated solution, Microchip offers the RE46C800 and the RE46C803. These devices provide all of the necessary analog, interface, and power management functions necessary to build a microcontroller-based gas detector. These integrated solutions minimize the need for many external components and provide a small, low-cost, and low-power solution for gas detection.